Welcome to this video. Today I will guide you through the wiring setup inside a dilution refrigerator. This is the dilution refrigerator. This is the machine you have likely seen in pictures of quantum computers. It is a crucial component that cools our qubit to a ultra low temperature, allowing them to function as quantum processors. Specifically, we will explore how the wiring system inside this complex machine works and how superconducting transmon qubits are controlled. Although the wiring system is complex, I will use a simple block diagram to make it easier to understand. Before we dive into the wiring system, uh, let's first understand how a transmon qubit is controlled. So this is a schematic of a single qubit setup. In this setup, this is the qubit transmon qubit. This qubit is connected to several key components. The qubit drive line. This is the qubit drive line. This is connected to the transmon. The this drive line is used to perform gate operation by applying microwave pulses at qubits transition frequency, that is 0 to 1 transition. There is also a flux bias line. This is the flux bias line. So this line is connected to the transmon qubit, and this is used for fine tune the qubit frequency by applying DC current, which generates a magnetic field. For today's transmon, which use squid loops, this squid this this squid loops use the external magnetic field that is essential for frequency control. When a current flows through the flux bus line, it produces a magnetic field according to the right hand rule. This field changes the effective magnetic flux through the squid loop, thereby adjusting the Josephson energy of the transmon. Basically, it operates the transmon frequency. Now, since this transmon qubit is a quantum system, we can't measure its state directly. Doing so would collapse the state due to the principle of quantum mechanics. To overcome this problem, a readout resonator. This is the readout resonator. So a readout resonator is weakly coupled to the transmon. This is the transmon and this is the readout resonator. This weak coupling minimizes energy transfer between the transmon and the resonator. The process works as follows. First, we set the qubit frequency by flux bus line, this line. Then we apply quantum gates by the qubit drive line to manipulate the transmon qubit. Finally, we measure the qubit indirectly using the readout resonator. Here's how the readout works. We send a microwave signal through the readout input. This is the readout input. This is the readout input. Readout input, and we use microwave signal around resonator's resonant frequency. Depending on the transmon qubit state, the resonator's resonant frequency shift. By measuring the voltage at the output of the resonator, we can measure the qubit state without collapsing its state. The entire setup enables us to control and read the qubit while preserving its quantum properties. So now let's now let's take a closer look at the wiring system inside the dilution refrigerator. This is the refrigerator. The cryostat s- setup includes four types of line. So basically, this is the simple schematic of this refrigerator. This is the room temperature, and this is also the room temperature, and these plates are the same as this. This is the 50K 4K 50K 4K steel cold mixing chamber, same. So there are four lines, that is input line, output line. So this is the input, this is the output. Qubit drive line, this is the qubit drive line, and this is the flux bus line, this is the flux bus line. So I will use a simple schematic here. This is the simple schematic, this is the simple schematic of this refrigerator. The actual setup involves more number of cables running through different temperature stages, but here I will show only one line. This is the one input, one drive, one flux line, and one output line. In actual machine there are a lot of this line. So from this is the room temperature plate. From room temperature to 4K stage, a stainless coaxial cables are used for readout input, drive line, and flux line. These cables have low thermal conductivity, which reduces the heat load on the refrigerator. For the output line, for this output line, we use copper nickel cables, as they strike a balance between limiting thermal and electrical conductivity. Below the 4K stage, we switch to niobium titanium superconducting coaxial cables for the output and flux line. For the output and flux line below the 4K, for the output, this prevents attenuation of weak signals, while for the flux line, it minimizes the heat dissipation from static bias current. Input and control means drive lines, on the other hand, continue to use stainless steel cables because the higher attenuation helps filter noise effectively. To ensure thermal stability, these cables are thermally anchored to each temperature stages, removing excess heat and ensuring local equilibrium. However, input lines introduce thermal noise from room temperature, also known as Johnson Nyquist noise, which can interfere with qubit operation. To mitigate this, cryogenic attenuators are strategically placed along the input and drive lines. So this is the attenuator, cryogenic attenuator. This in the gray box. This is the box. This is the cryogenic attenuator. So it may differ the total power. Here it's 60. This setup ensure operation in the low photon regime, critical for dissipative readout and preventing the qubit transition. So for that we use low attenuator. So here there is 60 dB of attenuation in input and drive line, and 20 dB of attenuation at the flux line. So flux line require less attenuation, around 20 dB, which is in the 4K stage to maintain flux tunability while minimizing resistance. At the mixing chamber, so this is the mixing chamber. Here, this one, the mixing chamber, a double junction isolator is used on the output lines. This is the double junction isolator. So this protect the qubit from back propagation noise, which is coming from the HEMT. This is HEMT, the orange triangle. This is the HEMT. So basically, it can the noise can back propagate from the HEMT. So double junction isolator remove this noise. Lastly, the EchoSorb filters. The EchoSorb filters. These are installed at the mixing chamber. These filters absorb unwanted microwave and inter- infrared signals, which cut off frequencies for a specific lines, approximately 10 gigahertz for feed lines. Feed line means the input and the input lines. Basically, this is the feed line and the drive lines, and 1 gigahertz for flux line to block high frequency flux noise. This one. Once qubit signal is pre-amplified by the HEMT, this is used for amplifying the qubit signal which is coming from the qubit, the output signal basically.